Hey everyone! Today is the last day of mirrors. I want you to be really good at these skills when you leave today. Maybe this will even help you a little bit with lenses. But to recap, there are going to be 3 ways that you can classify images. You can either memorize using a chart like this or similar, memorize which type of device makes which type, size, and orientation when an object is in certain locations. That's method 1. You could use ray diagrams, and you can use calculations. So let's review method 1. One way you could remember the types of images made is to simply memorize it. So a chart like this is good to have in your notes because then you can look up, is my device converging or diverging? Where is my object? And then classify the image as real, smaller, inverted, etc. Pattern here is that real images are always inverted. The closer you get to your mirror, the larger the object becomes, or the closer you get to the focal point. Another pattern is that converging devices, whether that is concave mirrors or convex lenses, any converging device can make multiple types of images depending on where the object is. Whereas any diverging device, like a convex mirror or a concave lens, we'll make the mirrors a different color so you can tell them apart, can only ever make a virtual smaller upright, no matter what the position is. So how you would use this is, let's say I got a picture like this and I asked you to classify the image. I would think to myself, first, is this a converging or a diverging device? Since the device that's drawn is a diverging mirror, then I know that it should make a virtual smaller upright image. That's my only choice. Method number 2. Let's say you don't want to memorize because, honestly, who wants to memorize? Right. Method number 2 is to draw ray diagrams. And ray diagrams are relatively straightforward once you learn the rules. So, a converging device takes parallel rays of light and forces them to be converged at the focal length. Whereas a diverging device takes parallel rays of light and the light goes away from a focal point. Those rays show whether a mirror is converging or diverging, right? So that's ray 1. Ray 2 leaves the top of your object and goes through the center of curvature. So in this case, ray 2 would go all the way down here. And see how those 2 rays are literally going to meet? They're going to meet like right over here-ish off page because I drew poorly. Well, that would be the top of the person's head. And with their feet on the ground, I'm going to draw them half off this page here. I see that I get a real inverted larger image. So using the 2 rays, I don't have to memorize. Though if you want, you can just go back and check. If you're between C and F, that's where the object is. Real larger inverted. Ta-da! Whereas if it's a diverging device, ray 2 is going towards the center of curvature, which, poorly drawn like the other one, center of curvature is like off to the right here somewhere. Center of curvature is like over there. Trying to get to it. So ray 2 and ray 1 do not meet in real life, giving you a virtual smaller upright image, which is good because that's the only one on the chart for a diverging device. But what I'm really going to have you practice today is looking at the 3rd method, being able to use mathematics to predict the images that are made. And you know what? We've already done all the math for this when we did lenses. It turns out the reason we're doing lenses and mirrors together is not only because they make the same types of images, And not only because we can do similar methods with ray diagrams, but we can still use all the same equations. So remember from Friday, we have our lens maker's equation that relates the focal length, the distance of the image, and the distance of the object. That's still going to stand. We've got our magnification equation. That's HI over HO. That will still work. You know what? We can also still use M is negative DI over DO for magnification. And we also know that the radius of curvature is twice as long as the focal length. So let's give us a problem here and remind us how to use all 4 of these equations from this unit. There haven't been a lot of equations so far, so these are the 4 that you should expect to be able to use. And someone did ask difference between center of curvature and radius of curvature. The center of curvature is the point at the center of this sphere. If we took your rear or side view mirror and made it a giant sphere, the center of curvature is a point, but the radius of curvature is a distance. And since everything's going to be in centimeters right now, we're just going to keep it in centimeters. Okay, so let's say I've got some sort of problem where I'm looking at a side view mirror and I want to check, I don't know, my face. I want to see something about my face. Maybe my hair is not looking great. And I know that the focal length of this side view mirror is negative 5 centimeters. And if you're thinking to yourself, why would that have a negative focal length? Well, that's easy. Any diverging device, either a convex mirror or a concave lens, any diverging device has a negative focal length no matter what the object is doing over here. And in this case, I'm the object. And let's say we put me at 15 centimeters, that's a pretty reasonable distance, in front of this mirror. Okay? And I want to use those to find all the other variables. I want it to find out where the image shows up. I want the magnification of the image. And I want the radius of curvature. Okay, so I'm going to put little boxes around the things I don't know, and let us math. The only equation I have enough information to currently use, or actually there's 2. Doesn't matter which I do first though. Let's do the radius of curvature one. The radius of curvature is twice the focal length. So in this case, the radius of curvature is 10 centimeters. And you can call that negative 10 if you want. Normally, radius, we keep it as positive. Normally, we like absolute value this, but not a big deal. It's 10 centimeters. Let's find where the image shows up. The image can be found using the lens maker's equation, and this is the one that I'm going to ask you be really careful on in terms of trying out your least common denominators here. You can't just take these and add them together, right? Someone looked at this and they said, well, can't I just cancel all the ones here and put 15 and that would just be like negative 20? No, you can't. You actually have to least common denominator this. So I'm going to least common denominator 5 and 15 to a least common denominator of 15. So negative 1/5 becomes negative 3/15 equals 1/15 plus 1 over di. Subtracting 1/15 to the other side, that's negative 3/15 minus 1/15 equals 1 over di. That's negative 4 over 15 equals 1 over di. And so let's cross multiply to solve. Di times negative 4 is equal to 15. Therefore, di is negative 3.75 centimeters. And if you are a person that needs reminding here, negative for an image distance means virtual. And hey, that meets up with over here. If di is negative, that means it's a virtual image. That's exactly what I drew for the ray diagram and what I would predict if I went and memorized that chart, right? Finally, let's get the magnification. Magnification, I can either use one of these two right here. I'm gonna choose to use this one since I don't know the object height to get the image height. So magnification is negative di over do. Substituting in, that's negative 3.75 over 15. And wow, that's not going to be useful for me checking out my hair or face because when I do the math out, 3.75, because those negatives cancel, divided by 15 is showing me a significantly smaller image. No units on magnification. My magnification is positive because negatives canceled. Positive magnification means it is upright. And that makes sense to me because not only was my image upright when I drew the ray diagram, but virtual images are always upright. So I'm glad that all follows. This 0.25 means that it is a smaller face, a smaller image than the original. So besides the checking like that all my parts are there, I think that this would be rather ineffective for checking like my hair or makeup here. Okay, because it looks smaller than the original. In fact, the reason your side view mirror says objects in image may be closer than they appear, well, that's because when your brain looks out the window and it looks at this side view mirror, it thinks to itself, that small car must be far away. But the car only looks smaller because convex mirrors make smaller images. Now, that's actually favorable for cars because we want a smaller image so we get a wider field of view. But what we don't want is to think a car is far away when it's not.
So before you go off and try this on your own, here are the 4 equations you should have written down at this point. We have the lens maker's equation that works for both lenses and mirrors, the radius of curvature equation that relates the radius of the sphere to the focal length that it produces. And one important point on F in both cases, both for lenses and mirrors, is that whenever you have a converging device, F is a positive number, and that's true for lenses and mirrors. Whenever you have a diverging device, F is a negative number. So now you have the equations you need to solve today's homework. Please remember to use a calculator. Please remember when you're doing the lens maker's equation to do your least common denominator. Show your work like you normally would on a regular homework assignment. And email with any questions because today is the last day we're working on lenses and mirrors. Best of luck to you. Bye.